In our previous video, we learned in general what a limit is, and hopefully you guys have written down a few sentences describing that way that you found it and the way that you're going to remember how to find it. And what we're going to do in this video is we're going to talk about the times that limits don't exist and how to identify them. So you'll get even better at this as we go, and I am very excited about it. So each of the following graphs does not have a limit at the indicated point, and so we're actually going to use Desmos. I've already graphed them just because it's going to take a little bit of time, but we'll sketch them on here and then talk about why the limit doesn't exist at those points. So let's go ahead and do that. So first and foremost, here is a piecewise function. And so we're looking at the limit of this piecewise function as x approaches 2. So if I switch on over to my Desmos that I've already opened up and graphed it on, we have this function. So here are the two pieces that I graphed. Whoops. And it looks like, so as we approach 2 from the left-hand side, I could say that my y value looks like it's also going to be at 2. But if I approach 2 from the right-hand side, my y value instead looks like it's going to be at 5. And so if I go ahead and just make a rough sketch of that on here, so if I approach 2 from the left-hand side, it looked like, oops, that was going to be an open circle. And then 2 from the right-hand side, it looked like this. So I had a pretty steep slope here, and then I had a pretty gradual slope here. It doesn't have to be perfect. We're just basically trying to figure out what's happening at 2. And so if I was going to describe why the limit doesn't exist there, I would say something along the lines of, because my left-hand limit, as I approach 2, right, that's this x value, as I follow my graph and approach 2 from the left-hand side, it looks like my y value is going to be a value of 2. But from the right-hand side, it looks like if I follow my graph and approach 2 from the right-hand side, it looks like my y value is going to be a y value of 5. And so because those numbers don't match, I would say my general limit doesn't exist. All right, let's go ahead and look at our next example. So in our next example, I have a sine function. Haven't seen one of those in a while, but sine of 2 pi divided by x, and I'm looking as x approaches 0. So I'll open up my next Desmos graph. Don't be alarmed. So this is what our sine function looks like. Basically, our sine wave, as we know, oscillates, and it goes up and down and up and down. And as we can see what's happening here, I have no idea what's happening as we approach 0, actually. I have no, I don't know what's going on. And so what we would say for this function is if you have an oscillating function where it just starts to get a little bit crazy. So if I was going to draw my function, this isn't going to be perfect, but I'm going to have basically it's just going to do a lot of that right in the middle and then something like that, right? So it does some sort of oscillation. If you have an oscillating function where you can't tell what's happening in the middle, there, that looks a little more put together, then you would say the limit doesn't exist there as well. You can find limits of sine and cosine and tangent functions, but just not when they oscillate so dramatically at the point or at the x value that you're looking at. And then the last one we're going to look at is this rational function, 1 over x to the 4th. So if I open up this Desmos graph, I'll notice that as I approach 0 here, my function is just going up forever on both sides. It's just going infinitely up. And so that would be another example of where you can't tell what the y value looks like it's going to be. So we would say the limit doesn't exist there as well. And so let me go ahead and graph that just so we can kind of remember. Just goes up forever. So no matter which way I approach it from, as I approach from the left or from the right, my graph is just going up for forever. There's no y value it's approaching. And so let's talk about these statements. So in letter A, we would say that a limit doesn't exist here because your left-hand limit doesn't equal your right-hand limit. So let's write that specifically using the notation. So we have limit of g of x as x approaches 2 from the left-hand side does not equal the limit of g of x as x approaches 2 from the right-hand side. So your general limit x approaches 2, just regular, does not exist. And we shorten that very often to D and E. In calculus, it's just recognized across the board. So the general limit doesn't exist because your left-hand limit doesn't equal your right-hand limit. In letter B, our example was that because our function oscillates at that value, so a limit does not exist if you have a continuously oscillating function. And maybe put at in parentheses, whoops, at the x value that your limit is approaching. Because it's okay if it oscillates other places on it, but if it's oscillating at the x value that you care about, so for example at 0 here, that was the issue. We could find the limit at -2, for example, but you can't find the limit at 0. Whoops. Okay, so it's continuously oscillating at the x value your limit is approaching. And then last but not least, if you have a function that goes to infinity or negative infinity, so a limit does not exist if the graph approaches infinity, and we can put plus or minus in front of that. Then that would be another example where your limit does not exist. Okay, so just kind of debriefing what we did in these notes. So we went through and we figured out that when you have a function that, even if the function isn't defined there, we can find a limit when it's defined as well, but even if the function isn't defined there, you can kind of see what your graph would have approached, and you would have seen that that's called the limit of that function. So there's a left-hand limit when you approach from the left-hand side, and then a right-hand limit when you approach from the right-hand side. And then if those two things are equal, then your general limit would exist. We looked at also some couple examples of when your limit wouldn't exist, and we'll explore these in more detail later. Eventually, we're going to just break from graphs altogether, and you'll be able to do it using just equations, just tables, and you guys are going to basically be rock stars at limits. So if you have any questions, please let me know. But other than that, make sure you have all of this down.